Hello friends, hope you're all having a great time. Today we are going to see if containers can be the future of Kubernetes. Thanks for joining me. I'm Deepu. I'm part of the JHipster team and a Java champion. I work as a developer advocate for Okta. I have built a lot of open source software. I'm a polyglot developer. I mainly work with Rust, Java, Go, and TypeScript. I have built Kubernetes dashboard called K-Dash. Please do check them out if you find them interesting. Let's start. So before we talk about containers, let's refresh our understanding of the container model on Kubernetes. I think we all can agree that Linux container technology revolutionized the way we all build and deploy software. Gone are the days of app servers and bare metal infra, right? Containers made it possible to have a portable and replicatable software and paved the way for large-scale cloud computing. So container technology tools like Docker and Kubernetes have become irreplaceable in any software stack these days. I don't think you will find any company that doesn't use Docker or Kubernetes these days. Technically, a container image, such as a Docker image, is a set of snapshots of a file system, right? These snapshots are layered together to form a single environment. So a container runtime unpacks these layers into a file system that is isolated from the host's file system. So to your application that is being containerized, this file system is the root file system, and the environment will look like an entire operating system, as the application wouldn't know the difference between the file system on which it is running and the host file system. So to it will look like an entire operating system. As long as it can find all the binaries and tools that it needs to run, then it is fine. It doesn't need the entire operating system there. Right? So on Kubernetes, there are two important layers that makes it possible to run these containers, right? So first we have the high-level container runtime called the Container Runtime Interface, or CRI. So stuff like Docker, Portman, and Containerd belongs here. They are all high-level runtimes. So second is the low-level runtime, or the Open Container Interface, or OCI. So stuff like runc, yoki, etc. belong here. High-level runtime makes use of a low-level runtime to finally run the containers. So let's look at the advantages of containers. I think we all know the advantages of containers over traditional deployment models or virtual machines, right? So let's have a quick refresher. Container images are lightweight compared to any traditional deployment model like app servers and stuff like that, right? They use less system resources than a virtual machine. They are highly portable. They are consistent and reproducible builds because they have Docker files and Kubernetes manifests and such things, which makes it very reproducible. They are faster to boot and run compared to a traditional virtual machine. They are easier to scale and manage, and they are much more secure than a traditional virtual machine. There are also other advantages, but these are the main advantages that we have come to love when it comes to containers, right? But there are also some limitations for containers, right? Container images are always an architecture dependent. That means we cannot use the same image across any OS and any architecture. We would have to rebuild the image for every architecture and OS that we need to deploy it on. Containers still need a lot of low-level OS primitives. Even though it is still much lighter than a traditional VM, it still needs a lot of operating system primitives. It does not provide a fine-grained control of the security sandbox. Though the container itself is sequestered and isolated from the host file system, it doesn't have a fine-grained control on what can be done or what cannot be done. There is no zero trust setup here. So this is where Containerless comes into the picture. But now let's see what Containerless is. So WebAssembly is what makes Containerless possible. So WebAssembly, or wasm, is one of the most exciting and underestimated software technologies invented in recent times, in my opinion. So it's a binary instruction format for a stack-based virtual machine that aims to execute at native speeds with a memory safe and secure sandbox. Wasm WebAssembly binaries are highly portable. They are cross-platform and language agnostic. So it is designed as a compilation target for languages. So once you build a Wasm binary, it can run anywhere where Wasm runtime is available. Though initially this was designed for the web, WebAssembly proved to be an ideal format for writing platform and language agnostic applications. Since the binaries are in a standard format, the WebAssembly runtime can figure out how to run it, and we don't have to worry about providing OS primitives and supporting libraries and stuff like that. It's similar to how you would run an app binary in your operating system, like any executable or DMG you run in your operating system. So a WebAssembly initiative known as the WebAssembly System Interface, or WASI, along with the wasm project, makes running WebAssembly out of the browser possible. Doesn't this sound a bit similar to containers? But WebAssembly is even more efficient. Since it's a compilation target for languages, you can write your application in any language and compile it down to a standard binary format, right? And this standard binary format can be deployed in a browser as part of a web application. And with the help of WASI, we can also deploy this in an operating system or an operating system running inside Kubernetes, for example. WebAssembly is even more efficient since it's lighter, faster, portable, and secure, and it can run at near native speeds. So this means that you can use WebAssembly alongside containers as workloads on Kubernetes. So with WASI, you can take a WebAssembly binary and run it directly on an operating system. So though originally this was part of the open web platform, WebAssembly has found use cases beyond the web. Apart from the browsers, it can be used in runtimes such as Node.js, Dino. It can be deployed in Kubernetes, cloud and IoT platforms, and so on. There are so many use cases for WebAssembly these days. This is what the Docker co-founder Solomon Hykes had to say when WebAssembly was gaining momentum. And he's on point. If wasm and WASI existed back then, we might have never needed Docker, and we might have directly started using WebAssembly for these kind of use cases. Let's look at some of the advantages of wasm and WASI. I mentioned some of this already. WebAssembly offers a lot of advantages, especially over traditional containers. Let's summarize them. So wasm modules are fast. They start up really fast. A wasm binary will finish execution before a Docker image is initialized. So they have near native execution speed. They have near zero cold start times, making them ideal for serverless functions. So with wasm modules, you can have real cold serverless functions without having to worry about cold start times and stuff like that. Wasm is extremely secure. They run in a strict sandbox environment with isolated memory. This is completely isolated from the host OS. It has a capability-based security model. WASI applications follow the principle of least privilege to reduce potential vulnerabilities. That means WASI applications will only have access to what exactly it needs. So it doesn't have everything by default. So wasm modules are memory safe and highly efficient due to its linear memory model. And if you're building wasm modules using language like Rust, for example, then you have even more memory safety. They are lightweight. So wasm modules are small in size. They use less memory and less CPU compared to a container. Wasm modules are also highly portable across operating systems, CPU architectures, and platforms. You can run wasm binaries in a browser, directly on the operating system, etc. Of course, with every technology, there are also some disadvantages. Most of the disadvantages have to do with standardization. So let's look at some of them, for example. In my opinion, the biggest disadvantage, apart from the standardization aspects, is that you can't just take an existing project and make it into a wasm binary, how you would Dockerize an application, right? With Docker, it is so easy. We have an existing application, we just write a Docker file, and we containerize the application, and then we can use it in Kubernetes or whatever. But you can't do that with wasm. You can't just take an existing application and you can't write a single file to make it into a wasm binary. So applications have to be built from ground up to be compatible with wasm, because it needs to compile to wasm, which means every library that you use, the language that you use, has to be compatible with wasm. Resource isolation is still not standardized. So there are some rough edges when it comes to that. Networking is still in the implementation phase. It is phase 3 now, but not standardized. For standardization, it has to go through phase 4 and phase 5. It is still phase 3. HTTP is possible with most of the runtimes, but HTTPS is a bit tricky. Network isolation is also not still standardized. Similarly, multi-threading is still in the works. For now, you can only do asynchronous implementation similar to Node.js. You cannot have pure multi-threading. This has to do with the fact that WebAssembly was designed for the web, where in the web everything is single-threaded. But work is in progress to bring multi-threading to WebAssembly, so that have a multi-threading in a container WebAssembly workloads on Kubernetes, for example, where you don't have the restrictions of an operating of a browser. And another thing to keep in mind is that WebAssembly is quite new, though not that new, but WebAssembly system interface, or WASI, is quite new, and WebAssembly on Kubernetes is even newer. So the ecosystem is still evolving. It needs time to mature. It needs more support from tooling and languages, libraries, and so on. Most of those runtimes have to do with the standardization, as I mentioned. So once they go through phase 3 and 4, those issues will not be a problem anymore. So let's look at wasm runtimes or WebAssembly runtimes. So WebAssembly runtimes are an integral part of running wasm workloads outside of a browser. So there are multiple runtimes to choose from. Let's look at some of the most popular ones. Wasm Edge is one of the most used runtimes, and it is integrated into most of the cloud-native tools like Docker, Podman, Containerd, Cron, Yuki, etc. So it is widely used in the Kubernetes ecosystem. It has WASI-like extensions, though it is not exactly a standard compliant. It has very similar extensions, which means you might have to work with wasm Edge in mind if you are going to deploy it with wasm Edge. It has support for many of the phase 3 WASI features like networking, etc. And it's a CNCF sandbox project. So it has great tooling for container and container, Kubernetes, etc. You can build Deepu microservices using that, a lot more use cases. You can also use wasm Edge standalone as a CLI, for example, or you can integrate it into your applications and run wasm modules there. And there are so many use cases for this. Other popular options that can be used as a wasm runtime on Kubernetes specifically are wasmtime, wasmer, spin, and slide. So all of them provide SDKs and CLIs. You can use them standalone or on Kubernetes. Most of them also have their own cloud platform where you can deploy microservices, for example. Spin, for example, is an entire microservice platform built on WebAssembly, so where you can deploy WebAssembly microservices with communication or networking features, file system features, and so on. As the de facto orchestration tool in the cloud computing ecosystem, Kubernetes have evolved and kept up with the advances in the cloud ecosystem. So it also kept up with advancements in WebAssembly so that it can leverage the advantages of WebAssembly on Kubernetes as well. So WebAssembly on Kubernetes is relatively new. It has some rough edges at the moment, but it is already proving to be quite revolutionary. So let's look at the existing ecosystem compatibility. Here we see a container tech that works with wasm. So if your Kubernetes distribution uses any of these underlying components, for example, if your distribution uses Containerd as the high-level runtime and Cron as the low-level runtime, you are good to go. Both support wasm. So if you're using Docker, it has built-in support for wasm. Similarly, Podman also has built-in support for wasm. And more Yuki has built-in support for wasm, and CRI also has support for wasm. And most of your Kubernetes distributions can be configured to work with wasm modules. But before you can run a wasm workload in Kubernetes, you also have to push your wasm binaries to a registry that supports OCA artifact. So wasm binary is considered is a first-class OCA artifact. That means any OCA compliant registry can accept wasm modules as well. So you can, similar to how you will build Docker images and push to a registry, you can build wasm binaries and push them to any of these registries. And when it comes to languages, not every language has support and the ecosystem required for wasm plus WASI. For example, while JavaScript runtimes like Node.js has support for wasm, it does not fully support WASI. There is some limited support but doesn't fully support WASI. So if a language supports WebAssembly, it does not mean that you can write a program in that language and deploy it using the WASI specification. The language has to also support the WASI specification. When it comes to Kubernetes, there are 3 ways to run a wasm workload. Let's look at them. The first way would be to package the wasm module as a Docker image with a lightweight Linux container. This is still lightweight and efficient compared to a classic container, but it doesn't give us all the advantage of WebAssembly because we are still running this wasm module inside a Linux container, which runs inside Kubernetes. It is better than classic containers, but still not the best that you can do. But it's the easiest way to start with. Second approach is to use a runtime that supports wasm workloads. For example, containerd, the combination of containerd with cron. So here, the high-level CRI runtime invokes the low-level OCI runtime, which integrates a wasm runtime to execute the wasm module. So in this case, containerd will use the containerd shim to decide if to run the workload as a standard container or as a wasm module. This is much more efficient and gives us all the benefits of WebAssembly. Third approach is to use a wasm runtime directly for wasm workloads. So containerd has a subproject called runwasi. So runwasi provides a containerd wasm shim that can interact directly with wasm runtimes, wasm edge and spin, for example. You can also use wasmer and any other supported runtime. So this allows containerd to bypass the OCI runtime altogether, providing us the shortest path of execution and better efficiency. And this is the most performant approach when it comes to running wasm workloads on Kubernetes. So this is almost like having a third runtime apart from the high level and low level runtimes. And of course, in this kind of setup, your normal containers will still be run by your OCI runtime, whereas wasm workloads will be run by the wasm runtime. So when it comes to WebAssembly, Rust is one of the best language and has the best ecosystem for WebAssembly, in my opinion. Because of that, I believe Rust is the best choice for building WebAssembly modules, be it for the browser or for Kubernetes or for WASI. Rust offers many advantages when used for WebAssembly. Rust's greatest advantage, of course, is its performance and memory efficiency, while offering all the benefits of a high-level language, along with zero-cost abstractions, memory safety, and thread safety, and all that niceties. And this is visible when writing wasm modules as well. You will experience all these benefits writing wasm as well. So Rust has first-class support for WebAssembly. There is great tooling and infrastructure and ecosystem around that. Rust produces the smallest, if not the smallest binaries, as it does not embed any runtime or garbage collection, etc. into your binaries, if you do with other languages like C# or Java. It has one of the best ecosystem WebAssembly, as I mentioned, and it has great developer experience and an excellent community and excellent developer tooling. In my opinion, Rust is the best language to write anything in WebAssembly. Also, most of the tooling around WebAssembly that we use in Kubernetes is built on Rust. For example, wasmtime, I think spin, wasmer, if I'm not wrong, slite. All these are built in Rust. You'll see a lot of WebAssembly tooling built in Rust. So let's see an example of a WebAssembly module written using Rust, which we will deploy into a Kubernetes container. Kubernetes cluster. Let's deploy Rust WASI app to a Kubernetes cluster. So I already have an application. Let me quickly show you the application. Okay, I have this very simple web app written in Rust. What it basically does, and let me make it slightly bigger. Okay, it's a very simple application. It uses a var for the web server part. So it basically generates random words. You can pass starting character or not. So it will generate a random word in English and respond that to your request. So it's very simple. So nothing much to see here. And when it comes to dependencies, again, quite simple. We use the WASI versions of warp and Tokyo so that it can compile to wasm. We have a Docker file. If you want to run this in Docker, you can run this Docker file and execute directly in Docker. We also have a Docker file to build and push this to OCI registry. We have a Kubernetes manifest file for this. So I'll come to this a bit later. So let's. Of course, you would have to add the wasm32 WASI target for Rust app, and you would have to build for this target. So let's first build this. So we have built this, And we can also run this locally using wasm. So this application is built for wasm because I'll be using wasm as my WebAssembly runtime throughout. So let's run this locally. So I have already installed the wasm CLI. So we can run this locally. So it's listening. So curl, it's running on 8090. The first time it initializes a database, and then we start getting responses. So this is running. This is, as you can see here, it's a wasm module running on wasm, right? Nothing fancy here. Now we can build this we can package this as an OCI image. For that we will use builda. We can also build OCI images using Docker, but I'm on Linux and Docker doesn't support building wasm binaries on Arch Linux yet. So I'm using builda for that. So using builda, we will build this into OCI compatible image or whatever. So as I showed here, this is the Docker file that I'm using for that. It's pretty simple. It just takes the binary that is built in my target folder and assigns a default CMD entry point. So let's build this. So it is built. Now I can push this to Docker Hub. So I'm using builda to push this directly to my personal Docker Hub with the latest tag. It is done. Yes. Now that we have built and pushed an OCI image, we can proceed to deploy this to Kubernetes. So I will use Kind as my local Kubernetes distribution. You can also use Minikube, MicroK8s, and many other distributions. So I'll use a project called kwasm to enable wasm edge support on my cluster. So you can use the same kwasm to enable wasm edge support or other wasm runtime support on many Kubernetes distributions. So let's create a Kind cluster. Let's create a cluster. So my cluster is being created. I'm going to monitor that using my tool, K-. So this is my tool built in Rust. It's a simple Kubernetes dashboard. So yes. Yeah, no, it's there. So my cluster is up. I have all my stuff in my Kubernetes namespace. I have simple single node cluster. So let's go ahead and enable support. So I'm going to use the manifest that kwasm provides to enable wasm edge support. So it's a daemon set that you can deploy directly. So once I do this, you can see here, it will start a kwasm initializer, which will add wasm edge runtime to your OCI runtime. In this case, I think it's running. It will enable cron underneath. It will also enable direct wasm runtime, which we can use to deploy directly to that wasm runtime, skipping the OCI runtime. So my wasm runtime is set up and done. So now I can go ahead and deploy my application, which we just saw. My Kubernetes manifest again is quite straightforward. You can see here I have defined a runtime class for wasm edge, and I have a deployment with 2 replicas. I have a specific annotation for wasm. I define my containers here. Again, though it is containers, we are using a wasm image. This is not a Docker image. This is a wasm image. So I'm using the image that I pushed to the Docker Hub. It's my port, and this is very important. I'm specifying my runtime class, which I defined here. So instead of running in my OCI runtime, this will run in the wasm edge runtime, which is the most efficient way. Then, of course, I have a service defined to expose this port via IT80. So let's go ahead and deploy this. The applications have started here, as you can see. It will take a second. So now they are running. Let me open a port. Okay. So now I need to use 8080 since I opened a port to that. So got it. Let's try. Starts with D. Yep. So we are getting this output from a wasm workload running in our Kind cluster. So let me close this. The future. right? So what does the future hold for wasm on Kubernetes? Good things, in my opinion. So the future of WebAssembly on Kubernetes looks bright. WebAssembly, Kubernetes, and cloud is still evolving. More platforms and projects are upcoming. There is a lot of interest going around. There are new companies in the space, Fermion, for example. So Rust has the best tooling and ecosystem for wasm, making it an ideal language to build WASI tooling, WebAssembly tooling for Kubernetes and cloud. We can already see this happening. We'll start seeing more and more Rust projects in the space. I think Rust already dominates the space in terms of projects. Networking, CLI, file system, etc., are being standardized. They are in phase 3. It won't be that long for it to go through phase 4 and phase 5 to become standard. Most of the runtimes already started supporting these. Machine learning and many other new features are coming, and containerless is definitely on the horizon. In my opinion, wasm workloads will coexist with Docker containers for a while. Docker containers will still be used for existing applications. There is still use cases for Docker containers. There is still value in that, so it's not going in. So I think both will coexist. New applications might decide to be wasm compatible from the get-go so that they don't have to build Docker containers. So they might go with wasm completely, but it's still evolving. So there are still a lot of chars and bugs and issues when it comes to wasm. While building, I originally built a weather forecast application for this demo. It worked fine on wasm edge. I used a weather API to fetch weather and pass it back, etc. But once I deployed that to my kind cluster, it was not able to make external calls because it couldn't resolve a DNS. So that's a bug in wasm edge, apparently. So there are these kind of issues. So it's still not at a state where you can blindly go and build and deploy everything as wasm modules. There's still some works to be done. There's still standardizations that needs to happen, bugs that needs to be ironed out. Cloud providers have already started using wasm for their serverless stuff because with its near zero cold start time, it's ideal for serverless applications. So that's it. If you're interested, join us on September 24th. For a 24-hour identity and security talks from Okta. It's free, completely free. Registration is open. So do sign up if you want to learn more about security and identity. And so thank you. Thank you for spending your time with me. Thank you for listening to me. Enjoy the rest of the conference. Have a good day. Bye-bye.